So I have a phone 14 or 15, whatever it was, they were just like in there. They were just echo cells. So the other people, these and stuff, this was that. Both of their families are right in that. Yeah.
Yeah. Oh, yeah.
Maybe it's
I know that's not.
She has good science that it's a hard machine we could color. I think that we're building super strong.
Yeah.
And so that knowledge gets served for I and we don't pass rate. Look at the site.
All right, I think we'll get started. Welcome to the AstroAI talks. Today, we're happy to introduce two speakers, and I believe today we'll be hearing a lot about Hamiltonian Monte Carlo. So the first speaker is Kangning Diao from Tsinghua University, currently visiting Berkeley, and he's going to tell us about synax, simulating the galactic synchrotron foreground with gradient. So, and then I'll introduce Matthew in a little bit. The floor is yours. And I'll remind the audience to interact with questions anytime if you feel like it. Thanks.
Thank you for a nice introduction. So today, I'll be talking about simulating the galactic foreground with gradient, basically for the inference. Okay, so first of all, the most exciting, one of the most exciting area in the following years or decades is a low frequency observation, radio observation, because we can see many valuable information from this band, including the galactic formation evolution, probably traced by the SK emit, and we will probe the astrophysics and cosmological information in cosmic dawn or epoch ionization with big interferometric arrays like Hera and SK low. And we will even plan to go to the moon to probe the 29 centimeter emission in the dark ages. So we can see the physics happening there. And then this is a non-exhaustive list. I can just easily list something like the seeking for cosmic birefringence or cosmic magnetism will be also benefited from the observation in this band. But however, unfortunately, most of these invaluable informations are buried in the synchrotron of our Milky Way. So in this plot, I show amplitude of different signals as a function of the frequency. You can see that ever since ever below 5 gigahertz, the synchrotron jumps over all kinds of signals, which means, and this plot is in log, it's in log scale. So which means the synchrotron is order of magnitude brighter than any other signal we want to observe. For example, in the right, I show a 400 megahertz Haslam map. We're supposed to see the 29 centimeter signal from post-ionization here, but all you can see here in this plot is synchrotron. And the synchrotron is 10 to the 4 or 5 order times brighter than the signal we want to observe, and that's a big problem. So we really want to remove it. But before we really remove it, what do we know now? Here I show, for example, our current knowledge about the synchrotron is still quite simple. Here in the left plot, I show a model inferred from the WMH synchrotron emission of the galactic magnetic field, which is one of the source of the synchrotron. While in the right, I show several simulated magnetic field in the zoom-in simulation of our galaxy, and you can see the huge difference between our inferred model and the simulation, which is somehow more similar to the real magnetic field of our Milky Way. And the reason for this is because we can model or represent these detailed structures, but incorporating them into an inference pipeline is very hard, because these including these features will typically require a huge number of parameters, even to the 10 to the 5 or 10 to the 6 parameters. So with so many parameters, there are several setbacks in the current inference pipeline. For example, here I show a classical MCMC pipeline. First, we propose a new parameter as a proposed state, and we forward simulate a sky map based on these new parameters, and we calculate the likelihood, and we reject or accept the proposed parameter at the current state, based on the likelihood. However, first of all, our current simulator is kind of slow, so we want to speed it up so we could do more inference loops at a given time. So we can have more effective samples to construct our posterior distribution. Another big problem is when it's about proposing these new parameters, because apparently random walk Metropolis-Hastings, because apparently we want the state we want to propose is something inside our posterior distribution. And every proposal we wanted to fall within this posterior distribution. But you can imagine that as the increase of your dimension, the volume of your posterior distribution will shrink to a negligible volume. So it is very hard to propose a state right in the posterior distribution with random proposals, such as the random walk Metropolis-Hastings. So this method becomes extremely inefficient. So, well, currently people have gradient-based sampling methods such as Hamiltonian Monte Carlo, for example, the method we'll talk about later. And these kind of methods are using gradient information to give you a better proposal right in the posterior distribution. But now we have this better proposal method, but the problem is where can we gain this gradient from? And the situation is the same if you don't care about sampling in posterior, if you only want to do the one best answer with optimizing. Gradient-free optimizing method is also inefficient. And you will need a gradient to speed up your inference with the increase of your parameter. Okay, so that's exactly why we release synax. The synax is built on top of JAX. So JAX bring us many exciting features. First of all, they bring us GPU and TPU support, so we could run our code on the GPU, which significantly improve the efficiency. And the JAX bring us automatic differentiation, so we can use this feature to gain the gradient with respect to the input. So we can not only simulate a sky map from input like electrons and magnetic fields, but we can also do the gradient-based inference together. And we will see how it revolutionizes the inference pipeline later. Okay, so let's introduce how do we compute how synax compute the synchrotron started by what do we compute? So the synax compute the sky map of specific intensity of the synchrotron denoted by I, and the polarized intensity, and the synchrotron is nearly 100% linear polarized. So we only need the polarized intensity of of linear polarization of two different directions, and denoted by Q and U. And these IQU maps are exactly the same as the first three Stokes parameters from the electrodynamics. Sorry?
Well, because of the Faraday rotation, oh, sorry. Yeah, that's really cool. So because of Faraday rotation, Q and U get converted together. Maybe you can come up with some invariance under the rotation.
We'll talk about the Faraday rotation later. Yeah.
Okay, good.
And let's start to talk about the mechanism. So the mechanism of synchrotron is basically very simple, just a high energy photons spiraling in the magnetic field. So it will suffer from Lorentz force, and Lorentz force will have acceleration. We know that acceleration makes radiation. So that's radiation comes from. And just like what you said, that we'll encounter Faraday rotation. So the synchrotron is partially linearly polarized, and this polarized emission can be decomposed into a left circular right polarized wave and the right circular polarized wave. And when they travel in the magnetized plasma, these two kind of waves will travel in different speed. So when they come out of the plasma, you'll see that when you combine these two circular polarized waves again, it's still a linear polarized wave, but it rotates. We have this rotation angle. So this is all the effects we need to consider in this calculation. And the ingredients we need is all here. First of all, we need the magnetic field, and then we need these high energy electrons. And at last, we need interstellar medium electrons so that we have to know the property of this plasma so we can calculate the Faraday rotation. And for each of these signals, the synax takes an analytical model or a three-dimensional field. For example, if we have an analytical model like this equation, we can compute the quantity of this field, this magnetic field at any given location in our galaxy. But sometimes we don't have this good analytical model, and we can just take a 3D field. If we have a 3D grid, we can interpolate. So we can still have the field value at given location in our galaxy. Okay, so here is how do we compute. So imagine our galaxy is contained within this rectangular box, and this bright red dot is the position of the Earth. What we need is to compute a sky map, but a pixel in a sky map represents a set line. So first we just choose set lines. For example, here we just randomly choose these 3 set lines, and the next thing to do is to substitute a straight line with points. We just segment a line into small pieces and collect the coordinates of the midpoint of these small pieces. So we substitute a straight line with those points, and we have the coordinate of these points, and we can calculate the field values in these points given our input. All right. Then we can calculate the emission and Faraday rotation happening exactly in each point. The very last thing we do is to sum in over the set line, so we get an integrated effect along a set line. And from this process, you can gain a sense that when you calculate one set line, it is totally independent from other set lines. So, which indicates this process is highly parallelized. So it is extremely suitable for some hardwares like the GPU. And here we first test our efficiency, and this is a runtime versus a total number of points we integrate. And you can see that the synax can integrate more than 10 to the 8 points within 100 milliseconds. And compared with the previous CPU-based code, previously people use a CPU to integrate, and they integrate 10 to the 6 points within 4,000 milliseconds. And this is a huge improvement. But our computing system is different, language is different, so this is not necessarily all the improvement by the GPU acceleration, and we'll talk about a more a better evaluation of the efficiency improvements later. Okay, so after we verify the efficiency of our code, the next thing we do is we want to test our inference pipeline to test the effect of synax. So so to do this test, we first construct a mock observation. We adopt 3 very simple models for the input fields. We adopt a YNW thermal electron model and WMAP cosmic ray model and WMAP B field model, and they all look very simple. And this is by the way, this is a slice. These are all slices in the galactic plane in a 3D field. So we have these models, and we calculate the polarized sky map, the Q map and U map. And here I only show Q for simplicity. And we add an independent Gaussian noise and to construct such a mock observation. And our task here is to infer the four parameter in this analytical WMAP B field model based on the mock observation we have. And we choose to test 2 different sampling methods. First is first of all is a gradient-based method, no U-turn sampler or NUTS. And another is a random walk Metropolis-Hastings, and this is a common method without a gradient. And first of all, we confirm that we run each method on CPUs and GPUs separately, and we first confirm that each method on each device will eventually result in a similar posterior like this. So this indicating that this posterior into the true value in the 1 sigma confidence region, so there is no systematic bias in this inference pipeline. And then we started to evaluate the efficiency. And we by comparing the same algorithm in different hardwares, we can conclude that here we evaluate the efficiency of different methods by the metric called the effective sample size per second. So, of course, a larger effective sample size is better. And what you really need to do is, what you really want is the minimum effective sample size of one of your parameters beyond some threshold. So the really metric to compare here is the minimum effective sample size per second. So here I denote in the purple circle, and you can see that from the values here, you can see the CPU gains a roughly 20 times improvement compared with the GPU gains a 20 times improvement compared with CPU. And it is worth noting that the GPU here is Tesla A100, and the CPU here is AMD EPYC, and they have the same price at this time on Amazon. So this is a fair comparison. Yeah. So now you know which hardware to buy when you have money. Yeah, and from the same algorithm from the different algorithm on the same hardware, we can roughly conclude that on such a simple 4-dimensional model, the nuts gain a 2 times improvement on compared with a random walk Metropolis-Hastings. And if we test our inference pipeline on 16 parameter model, the number of parameters is still not very high. And this 16 parameter B-field model is achieved by stacking 4 very simple WMAP B-field model. And we simulate a map like this, and all other fields, including noise, is similar to the previous mock observation. And we use the nuts to infer the parameters here. And the nuts took less than 4 hours to finish 1,000 iterations. And the effective sample size is reported here. And you can directly look at the minimum effective sample size is of order 10 to the minus 2 per second, of course. And well, the random walk Metropolis-Hastings totally failed in this test case. So the synax completely outperformed the gradient-free method in this case. And you can imagine that if we continuously using a more complex model with more parameters, the synax will be even better. Cool. And sometimes we don't have a good analytical model of the field, so we need to deal with the 3D grids as the representation. In this case, we could do the optimization with gradient. In this case, for example, we have this mock observation, and we optimize the 3D B field to get this based on this mock observation. So here is the sky map we reproduced with our optimized B field. You can see that this is almost identical to our mock observation. Well, the good news here is it proves that our the gradient-based optimization is powerful. It can be effective on complex representations such as 3D grids, but we have too many flexibility so that we even reproduce the noise features. So this is annoying. You can see from the optimized B field that this is highly fluctuated, and we see the degeneracy along the left side. So this means if we really want to use synax to optimize the B field based on the observation, there might be some work to do to apply regularizations to prevent this overfitting. Okay, so the last funny experiment we do is we directly optimize the B field based on the Haslam map, and in this plot I show the optimized Haslam optimized total intensity based on the Haslam, and here I show residual, and this is residual PDF. You can see the residual is really small compared with the typical amplitude of the signal. However, we encounter the same problem. Our optimized B field is highly fluctuated, and we see the degeneracy along the left side. So this is just a simple experiment to show the superiority of synax, and although I think we're first group of people to to faithfully reproduce a Haslam map, although our answer is wrong. Well, so how do we possibly improve this in the future? It's a little bit about the future perspective. So, well, as we talked about just now, there is an effect in the polarized synchrotron called the Faraday rotation. So the emission in the different places in the galaxy will experience a different Faraday rotation. This is characterized by this quantity rotation measure, or RM. What this quantity really means is different RM means your polarized spectrum will oscillate differently with respect to the frequency. So you can see here, I show an example that a 10 RM emission is the spectrum of 10 RM emission is very different from the spectrum of 50 RM emission. So now we can expect that given enough observation channel in this polarized observation, we are likely to break this degeneracy along the left side. So this is what we need to focus in the future to study. Can this really break the degeneracy along left side and give us a reconstruction of the galactic fields with high fidelity? Okay. Okay, so this is a small extension of about synax. So, well, previously we were talking about simulating our galaxy, but of course, the synax can be also used to simulate the small patches of a sky, given the flat sky of approximation. So the only thing you need to change in this scheme is you need to change the direction of those sidelines. In this case, all the sidelines point in the same direction. So we can simulate. We can quickly simulate an extragalactic object given the synax. So perhaps if we have enough data with good quality, we can infer the 3D structure of those small patches in the future. Sorry.
Yeah, these are really cool. So I was wondering, what is the population of electrons that you actually consider in your mock data? I think you said thermal electrons, right?
Yeah.
So I can imagine because of the black body spectrum and things like that, having those thermal dominant emission would be good, but you can also imagine to have a correction to it that would be not thermal, for instance,
yes.
You know, non-Gaussianities and things like that. So since you're really hyper precise in terms of magnetic field and those structures, did you check how much it could affect your reconstruction and polarization? Because I think based on the similar intuition that we have from event horizon telescope collaboration and completely different scale, those population may affect linearly, at the like dominance basically level to the map and structures.
Oh, I see. This is a good question. We haven't considered such an effect yet because this is I crafted this just several weeks ago, so we will look about that later. Thanks for your comments. That's really
sure.
Yeah. So okay, so here comes our summary. So here we introduce synax as a quick simulator with the access to the gradient, so that we can deal with more parameters in this inference problem. We can deal with much more, and based on our current results, the GPU acceleration brings us at least 20 times improvement in computing efficiency, along with the access to the gradient. And the gradient-based sampling is 2 times faster than random walk Metropolis-Hastings in a small dimensional, very simple 4-dimensional model. And since those gradient-based methods have better scaling as the increase with as the increase of parameters, we can expect that they will be even better with the more complex models. Okay, so this is a QR code of our documentation, so feel free to scan it and play a bit with our model. Thank you.
Any questions? Yes.
Thanks. Very interesting. I would like to raise a point of caution similar to what has been mentioned before. If you look at the Faraday depth in the Milky Way, it is very small.
Yeah.
And the reason is that we have all these field reversals that happen locally. If you look at the solar neighborhood, right, there's a local bubble, there is all these other bubbles around. They interact, the field is typically aligned with the walls of these bubbles. And so if you calculate the Faraday rotation, for instance, against extragalactic background sources, has been done in the Buchenwald map, which we try to reproduce in Heidelberg. You see that it flips all the time. So with these large-scale models, you can never beat these degeneracies and these local features. So you also mentioned the Patmore map, right? Aurige 6, etc., etc. So if you really look at the Faraday map of the Aurige ones, they fail. They fail big time reproducing the actual Faraday sky because they do not have these small scale fluctuations. So if you really want to catch that, you need a galaxy model that takes this into account, either numerically or in a statistical sense.
I see.
And so I think that is something you should very much try consider.
I see.
It could not be difficult to at least put a few bubbles in a statistical manner, but that will dramatically change the outcome of your Faraday rotation calculations and the Faraday depth you get.
I see. Thank you very much for the comment. I'll definitely look at it.
Thanks. Any other questions? Yes.
For others, also contribute. Yeah, but actually, going to your question, sorry, that's comment to comment. For instance, people always do it like external Faraday rotation. So I think that there must already be some pipeline, that you could just very much easily use. I'm part of the ESG, but I'm not observer, in the sense that I can help you. I think maybe you can just ask them, if your focus is on the Milky Way, that should be just some pattern that you just subtracted,
Yeah.
Just very quickly, so all the results you showed in terms of the inference of these parameters was based on the simulated mock observations.
Yes.
Have you tested this on data, or is there a plan to test this on actual observations?
Yes. So our plan is to verify if synax can really break the degeneracy of along line side based on the galactic observations. If we can really prove that in a simulated case, we'll apply our code on some real observation data like XPath or something. They already have some polarized data at the frequency of like 5 kHz.
Thanks. Comments, questions? So you're going to be staying here for the rest of the day. If anyone wants to touch base at the end of the talk, can touch base. So I think we can now. Thank you very much for standing again.
Thank you.
Moving on to the second talk today by Matthew O'Callaghan, who's visiting from the Institute of Astronomy, Cambridge, UK, and he's going to be telling us about Hamiltonian Monte Carlo with normalizing prose, which is a very interesting generic title, which means it's going to be useful for everyone here. So please.
Oh yeah. Where'd you go? Yeah. Thanks.
All right.
Thank you. Yeah. Cheers. I'll just wait for the microphone. Yep. You can. You're fine. Flip it, and then I just flip that. Is that okay? Can everyone hear me okay?
Yeah.
Okay, great. Okay. I'm really happy to be, so let me start my time. I'm
I'm really happy to be following that. Excuse me. I'm really happy following that talk because my talk will be on Hamiltonian Monte Carlo and normalized inflow priors. And now I don't have to convince you that GPU accelerated Hamiltonian Monte Carlo is really good. Okay, because thank you very much for that. But as astronomers, I think all of us should have a Bayesian toolkit. And in this talk, it is quite general, but what I'm going to try to convince you is it's more like a theoretical workshop. So for people who are used to using kind of machine learning methods, I hope I can convince you that this is something that you can usefully add to your Bayesian toolkit. And maybe for people who are just starting out with machine learning, I can hopefully convince you that a theoretical workshop is worth it. Really what we want to look at today is just a few things. Thankfully, I can kind of go quickly to the Hamiltonian Monte Carlo now. But I want to start by just talking about Bayesian inference in astronomy and really why that's important to all of us. And then I'll move on to looking at Hamiltonian Monte Carlo and particularly its gradients. And then talk about normalizing flows and how they're already used, particularly in Bayesian inference in astronomy. And then look at how what we're going to propose is something slightly different. Hamiltonian Monte Carlo with normalizing flow priors. And we'll see that this is going to add some restrictions. And particularly it's going to have some allowed architecture. So there'll be some architectures which won't be allowed and some architectures which will be allowed based on how we want to be able to implement these priors. And then finally, we'll show with some mock toy data that we can use this for inference, but we need to be very careful. Okay, so I assume as astronomers, many of us have come across Bayesian inference before. It's essential when we deal with noisy data, okay? So the goal, the goal of any Bayesian inference is to find the distribution of some parameter given noisy data, right? Okay, so me, for example, I work with high galactic latitude reddening. And for example, we have priors such on the HR diagram, and we want to infer parameters given noisy data. So common methods that we'll all have seen before is just standard Markov chain Monte Carlo, which we've seen, approximate Bayesian computation, simulation-based inference, and nested sampling. So these are all great methods of inferring a set of parameters or any other parameter in a Bayesian framework. But in this case, we're just going to consider the simplest problem. So it's just a direct noisy observation of a parameter with a defined prior. Because we want to consider this as how you can kind of build it into your existing framework or existing hierarchical model. So for example, to think of this, if you have some distribution about what color magnitude vectors look like for a cluster, and you observe noisy data, you might want to infer what the true magnitude is. Many people don't do this, but this is just a kind of an example, a simple example, and we can kind of generalize this later. Okay, so we've seen already what Markov chain Monte Carlo is. So in particular, our goal is to propose, is to generate samples from a posterior distribution of a given parameter, given that we've seen data. And Hamiltonian or regular Markov chain Monte Carlo, such as Metropolis-Hastings, can struggle. Okay, and that's because it does a random walk process. It jumps, it tries to find a new parameter, it evaluates the probability of that and either accepts or rejects it. And as we've seen already today, Hamiltonian Monte Carlo is a method which really speeds this up, and it's based on gradients. In particular, it proposes Hamiltonian dynamics to replace a random walk. So instead of just jumping like small Gaussian shells around parameter space and looking for new parameters, it employs Hamiltonian dynamics and operates by evolving the system in the parameter space to propose a new parameter, and then we either accept or reject that parameter based on posterior ratio. So samples eventually, theoretically, will be generated from a tree posterior. So a theme you might get from this talk is that I really like theorems. I'm a bit of a maths nerd, and this is one of the things that I really like, and why we kind of chose Hamiltonian Monte Carlo mixed with normalizing flow priors, as we'll see. Okay, so for anyone that's not familiar with normalizing flows, they're based on the density estimation based on the change of variables for probability distributions. So this is, I really like this because it's a really nice way of machine learning that it's kind of informed. Okay, so we know theoretically under some assumptions that we can construct bijections between a data space and some parameter space, which we call Z, which we usually define a base distribution, such as a standard normal distribution. And we want to learn how to learn a bijection which maps our data onto that distribution, or vice versa. Because it's a bijection, it goes both ways. So the goal ultimately is to define a bijection and then learn the parameters of that bijection. An important consequence is that we want to make this, some people want to make this easy to sample, some people want to make this distribution easy to evaluate. It depends on what your problem is. Very often, and almost always, we want to make sure our Jacobian term, as you can see in the second equation here, must be able to be evaluated well, because Jacobians are just difficult to calculate, and there's just a lot of parameters to try. And so we learn these distributions by minimizing a KL divergence between the base distribution in this Z space, which is the normal distribution, and our data space distribution. Okay, so in this talk, we're going to assume that we've learned the distribution well. I don't really mind about how we learn these normalizing flows, but I want to assume that we've learned one well, and then how can we implement those as priors and perform inference over that. Okay, but we're going to particularly care about a type of normalizing flow architecture called autoregressive normalizing flows. The results presented here can also be applied in coupling normalizing flows. Many of the ideas are the same. In this talk, I'm trying to convince you that you need to look at the architecture when you're implementing this and be very careful about how we implement it. It's not just blindly apply these normalizing flows, it's about being very specific. So we're going to get into some maths now, but we're going to do this. For normalizing flows, autoregressive normalizing flows, we propose a bijection, and we care about the bijection at each point or at each dimension of your data vector, right? And so for autoregressive normalizing flows, we have two key components. One is the transformer, and the transformer operates on each component. And the way to think about the transformer is think about just an affine function, like y equals mx plus c. We want to learn the parameters. In our case, this would be m and c. So we have a bijection, which is the transformer, and then we have a conditioner, which aims to use your data to learn the parameters of your bijection at each dimension. Okay. Very importantly, your conditioner, which is what learns the parameters of your bijection, depends only on all parts of your data vector less than that component. So for example, we have a bijection, the third component, the parameters of the third component of your bijection would only depend on the first and the second component of your data vector. This is really important for two reasons. One, it allows because this will give us a lower triangular Jacobian matrix, it allows us to factorize the Jacobian really nice. Another reason is that this has some theoretical advantages that under certain assumptions, we can have universal approximators of density functions. So under some kind of basic assumptions about our architecture, theoretically, we can model any distribution. Okay. Okay, so normalizing flows have been already used in Bayesian inference, but what we're doing is something slightly different. So simulation-based inference or likelihood-free inference is really common at the moment. It's proven to be a really amazing way of using simulated large-scale simulation models and try find or derive posterior distributions in a different way. So this is not a Hamiltonian Monte Carlo method, but what this does is we try to use a normalizing flow to learn the likelihood function directly or learn the posterior distribution. So this is slightly different in that we have, I suppose, an ideological difference, which I'm calling it, which is that we want to learn prior distributions using normalizing flows in the same way that before we might use, just standard density estimation, more classical density estimation to learn a prior distribution. Yeah.
This might be a very, very, very naive question.
No, please.
So why is it that you need to learn prior? In the sense that I would suppose that you're just encoding any information you have before you've seen your data. Mm-hmm. What do we really mean here by learning the prior? Are you assuming that the prior needs to have a particular functional type, or what is? Yeah.
For example, let's say more. It's not in terms of the simulation base. Say we have loads of simulations, and for example, loads of isochrons, and we want to learn. It's a really complicated high dimensional space. Instead of having this as a deterministic model where we then incorporate priors over that, we can simulate these isochrones and directly learn that space using the normalizing flow. Does that answer the question? Great. Okay, so this can be really difficult to do because in Hamiltonian Monte Carlo, we need to take derivatives, as we talked about before. And so we can expand out derivatives, but it's very important that to use this, we will end up needing to use a second degree derivative for the Jacobian. And that is not necessarily easy because a lot of the architectures that already exist only really require a first order derivative. Okay, so we also want this second order derivative to be continuous because otherwise when we're in a Hamiltonian Monte Carlo sampler, we might get, as it's moving through parameter space and it's evolving, we might get stuck in a different kind of knot. Might have some sort of problems. Okay, so another big equation of maths. Apologies for this, but I'm trying to convince you also here that this is important. The mathematics behind all of this is essential, and we need to do this, and we need to understand this to be able to correctly implement it. So there will be a paper out hopefully by the end of the week, which is going to go to this in more detail. But what I want you to see here is what we're looking at is derivative in a given direction, and what this derivative does is it tells us how the log posterior is changing of the normalizing flow in a given direction. Okay, so I don't really want to go through all of this equation in a step. I'm going to pull out the bits which are important for us on an implementation level. Okay, so what I'm just considering here though is the derivative with respect to x alpha in a given direction. So these are the things which actually matter. Okay, and I can convince you this when we kind of publish the paper. But what we really need to do is we need to look at the transformer, and we need to look. So remember, the transformer is the bijection itself, and the conditioner is the neural network which spits out the parameters of that transformer. Okay, so we need the transformer to be second order continuously differentiable with respect to the first parameter. We also need a transformer to be first order continuously differentiable with respect to the outputs of the conditioner. And finally, we also need the conditioner to be first order continuously differentiable with respect to x alpha. It's important here to notice, which was included in the last slide, that we're called that x beta here has to be greater than x alpha because conditioner depends on it depends only on values less than beta.
Question.
Yes.
Maybe
Yes, please.
I'm sorry, but why do you need to be second order derivative continuous?
Okay, great question.
General or for?
No, so this is exclusively for implementing normalizing flow priors in Hamiltonian Monte Carlo. So apologies. So if I go to the previous slide, we want to look at so in Hamiltonian Monte Carlo we need to have the log probability which needs to be differentiable to be used in the gradients. And for that to happen, the actual transformer, if we evaluate the gradients, needs to be second order differentiable. Otherwise, what happens is as we evolve the Hamiltonian dynamics in the sampler, it can get stuck because you're going to get discontinuities. Yeah, so it has to be second order. Okay, thank you for the question. I mustn't have clarified that correctly. Okay, so this is what we need. So as we're implementing this, we need to be able to define our architecture such that it meets this requirements. Otherwise, you're going to get there's going to be some serious problems. Okay, so in terms of the conditioner.
Sorry.
Yes, please. Yes, sir.
I thought you said a few slides ago the transformers are, sorry.
Sorry, yes.
I thought you said a few slides ago that the transformers are linear, like half-wave transformers.
No, sorry, apologies. They can be linear. I was just using that as an example
Okay,
of yeah.
because you're taking second derivatives of a linear.
Sorry, yes,
balance, and I was just okay. So they are linear.
So yeah, to clarify, there has to be any bijection, and the conditioner parameterize that bijection. So I said for example, if tau is a linear function, the conditioner will control the parameters of that linear function.
Okay.
Okay, thank you. Okay, so let's try to think about what this means in kind of implementation wise. So we need our conditioner to be C1. Okay, so let's continue to the first order.
Sorry to interrupt you.
Yes.
Just a follow-up.
Yes, please. Yeah, please. No, I'm really glad for this.
What if it was linear functions, then the second derivative is?
Yes, we have slides, a few things.
Sorry.
Yeah. Thanks, though. So yeah, the first thing we want to do is consider just the conditioner. So that is what's going to output the parameters of our bijection. Okay, so what does this need to be? So we know from the previous slide that the conditioner needs to be first order continuously differentiable with respect to x alpha. But let's just say for simplicity, I mean, we all know neural networks scale very nicely as we build them up. So we're just going to deal with it. It's outputting one parameter. If we take the derivative, this requires that our conditioner needs to be, we just need that the activation function needs to be C1, okay? So for example, ReLU1, okay, which is, this is important, this is really important because as many architectures just will throw in ReLU as by default, okay? So as you implement this, you're going to get a serious problem. And as I was testing this, it can be really problematic. For also example, things like PyTorch, sometimes stop overflow. They add, they turn it into a piecewise function. Again, this might be fine, but it also might not be fine. If you're dealing with really high dimensional parameter spaces, it's hard to know if you've just hit a discontinuity or you've got a right answer. So we just need to be super careful about this. So also, it's also important to recognize that some architectures just have problems. You might want to add regularization to control, the gradients. You might want, as you expand to different levels, your gradients become really large. Or you might, so ideally you want to be able to learn it, but you also need to be able to help your model learn. Okay, so this is the conditioner. The conditioner has the least amount of constraints in it. Now, transformers. So we need to go through a few different types of architectures. We have to deal with all of them individually. I'm not going to do that here, so I'll refer later to the paper which which will help us understand all of them. But I've just done two architectures which will work and one which won't. So for example, fine flows. We will see that we'll go through some equations. So fine flow is just a linear bijection, and then the conditioner controls those two linear parameters. Second derivatives disappear. Okay? Yeah. Please.
Can I ask? So I'm wondering what you do with priors that have sharp edges. And that is something we struggle enormously with when we do our normalizing flow invertible neural network approach. If you have sharp edges, let's say in the extinction, right? The extinction is 0 and it cannot be negative. And this causes all kinds of problems for us. And so I was wondering how you deal with this type of.
That's a really great question. I think maybe we could talk more about it after, but I'll give a quick answer now. So again, yeah, because the discontinuities really help sharp edges. So that's a huge problem. But certain architectures, so there's a type of architecture called smooth normalizing flows, which they operate as a sum of bump functions. We find that that's pretty good at creating sharp edges. The difficulty there when it comes to an implementation wise is that sometimes you get really strong gradients around those edges and it's really hard for the sampler to go up. But we find it can do that. It's just about managing it. We find often that scaling things between 0 and 1 really helps, and making sure that we don't get kind of controlling the gradients on this front, like putting regularization on the gradients. But these bump functions, some of these bump functions seem to be quite useful for hard edges. However, getting it wrong with the bump functions can be really problematic in that we just get, if it doesn't learn properly, you can just get sharp edges where you don't want sharp edges.
So in the end, it's just trial and error in these cases and see what works for your particular application, right? Yes,
there's definitely no one thing fits all. And I'm finding that we find that the next flow that we'll talk about, which is the neural network-based flows, are really useful for us. But they do, we'll actually see in an example, they do find it hard to learn that really, really sharp edge. Yeah. Okay, great. Okay, so this is one of the type of flows that I'm most interested in, which is a combination-based flow, which follows the idea that if you have monotonic functions, allowing this invertibility, so you have a sum of monotonic functions, which will again be monotonic and therefore bijection. So we model this by using just a simple feed-forward neural network as a flow. But the way that we can actually use this is just requiring certain constraints, such as the activation function of this needs to be continuous and monotonic, and the weights need to be positive. Okay, so this gives us a nice flow, and it's really flexible. And the reason we like this is that we don't need to worry too much about invertibility in Hamiltonian Monte Carlo. So we don't really care too much about sampling. We need to get a rough sample for the sampler, a rough sample from the prior for the sampler to start working. But mainly we care about density estimation in Hamiltonian Monte Carlo, okay, and its gradients. So for neural network, so neural regressive flows, they don't give you exact samples, but they can potentially give you exact density estimation. So it's a really strong, so they do satisfy the universal density approximator, but in Hamiltonian Monte Carlo, you need to sample, you don't really need to get exact tractable samples, but you need exact tractable density estimation for the sampler to work. And that's sampling with the prior. Okay, so these are quite nice. The only real constraint that we find that we need to implement in this is that the activation function needs to be C2, and it needs to be monotonic. So for example, the Gaussian air linear unit won't work if you want to replace it with the linear unit. We tend to use either tan H activation, hyperbolic tangent activation functions, or signal activation functions. Okay, again, just kind of reiterating here that some people will implement this as these activation functions as having certain properties to stop overflow, such as the soft plus, which can work as properties to stop overflow, which will add a discontinuity that you don't want. Okay, so something which doesn't work, anyone who's used spine-based flows, so this all came from me trying to implement a spine-based flow and realizing why it wouldn't work. Because some rational quadratic spine flows is a bijection which learns knots and derivatives to generate a bijection, and it uses the conditioner to find those knots and those derivatives. However, at every knot, you get a discontinuity in the first derivative. And so as we need to take a second derivative, this becomes a huge problem. And you can see here where we get these discontinuities. So the spline flows are always C1. And so as we try to do inference here, we'll get a serious problem. Okay, so to finish off, I'm going to give just a few examples of what this inference actually looks like and why it can look really wrong. And so I haven't really pushed the limit of actually training to make sure this looks perfect. I'm more trying to make sure this normalizing flow looks it is a learned architecture to show you that it fails based purely on the architecture itself. So what we've done here is we've simulated the Gaussian just a point at -4,4, so kind of in a strange region of parameter space. And we've tried to infer that assuming some Gaussian light field error. And so the errors in this plot are the gradients of the log likelihood at that point. And what we find is that the sampler simply just can't get to that space. It finds a little valley where the stitches are and gets stuck there and just keeps sampling there. You can find tricks of getting to flush out, which is great in 2 dimensions, but as we get to higher dimensional spaces, these knots just become everywhere, and you'll really misunderestimate your errors. And it'll be really confident about a solution, even though it's wrong. So that's a huge problem, of course, if you want to do this as part. But we can see that this does work, and it's got a different plot. So what I've done here is I've modeled again the Gaussian. We've modeled normalizing flow now using a block neural autoregressive flow on a three component Gaussian mixture model. And so we've done this inference again using the 0.01, which you can see just here, that. And we can see that the inference works pretty well. So it's learned the gradients. There's a bit of an issue in the center, as you can see. That's more just a fitting problem. It just hasn't learned the density perfectly well. But we can see that it can sample really well, and it's able to sample kind of a multimodal distribution quite nicely as well. So it can move, the sampler is allowed to move around the distribution and you can get realistic samples. And we find as we move to higher dimensions, the same thing happens. We're able to get really nice inference using normalizing flow priors, and we have to generate really nice posterior samples. We also find that it's pretty quick because it can be implemented in JAX and it can be implemented on a GPU. And also it samples quite nicely because you sample in this Z space, as I was saying. So you're sampling in, and because normalizing flows learn a bijection between your data space and a really, really simple Gaussian normal space, it can sample in a multimodal distribution quite nicely because it's sampling in a very simple distribution, and that's evaluating its gradient in a given space. Okay, so to summarize, this is, I hope, a nice addition to your Bayesian toolkit. It's not going to work every single time, but it's something to think about if you want to be able to include something differentiable in your Bayesian pipeline, and you already have, for example, using NumPyro, where you can, or you're using another Hamiltonian Monte Carlo inference algorithm. It's really great. We're finding that it's working really nicely for certain problems, but again, we need to proceed with caution. We find that if you implement this slightly wrong, it becomes a bit of a rabbit hole finding where this discontinuity arises from, but we'll give you just one answer. And that's, at high dimensions, it's really hard to diagnose this unless you make sure that you kind of get your mathematics right the whole way through. So hopefully by the end of the week, we'll have our reference paper, which just goes through all of the different combinations and architectures, which work nicely as something that you can kind of refer to and when you're doing your own implementation. And so if we have any questions, yeah, I'm more than happy to take them.
Thank you, Matthew.
I can ask a question.
So this is a quick question, I was just wondering, the issue with the stitches, that's at least detectable or diagnosable if you just start with different initial conditions, right? Or do you feel like that's?
Yes. So for example, if you, sorry, I just mentioned this. So yes, for example, if we're actually going to the same space, we can find quite a nice region in here where things work pretty okay. However, if sometimes you just get like you can see down here. So if you're operating in a space where there's a stitch, in high dimension, it's quite hard to find where they are. And one thing, we actually originally started using these, and what we did is we looked at the second. You could just do a flag by looking at the second derivative of the log probability, and you just get like a 0, or it would go crazy. And if your samples fell into that region, we would just flag it and say it's wrong. So you can find out if it's going to cross one of the stitches. Within those stitches, it works pretty well. But if it ever has to cross a stitch, and I said in high dimensions, it's quite, those stitches, as dimensions increase, they just start to intersect more, and there's more regions where it's kind of hard to find. Then it becomes a big problem. But in theory, in between the knots, it's technically completely fine.
I guess, sorry, my question was more that I guess we start with like different, like enough different initial points or in different basins, you
Yeah.
realize because you'd be converting or stopping in different stitches. Right?
Yes, yeah. So for example, so do you mean like so there's a bit of a stitch here.
Yeah, so presumably if you started somewhere there, you'd end up at a completely different point.
Yes, yeah. So if you start on either side of the stitches, you could, but it ends up being, we have to use a lot of chains, and you start to get it, and then you also just miss. It becomes quite nasty because also the stitches end up having like, I think they misrepresent probability in like the neighborhood of the stitches as well. So I think there was also that issue, but yeah, in theory, you can just like kind of almost treat it as sample like 20 chains, and they will start to sample around the correct place, but you will still have a line where it's not going across that well.
So I have one follow-up. So when you're talking towards the end about checking whether certain architectures or diagnosing whether they have such issues, do you do that mostly empirically, but checking whether the gradient of your log probability has these issues, or do you do that like mathematically or using the architecture?
I did it mathematically for pretty much all the main architectures. And I mean, I started doing it empirically until I realized that there was just trends, and then I realized that sometimes I just need to figure it all out, and it ended up being the solution ended up being quite simple. There's just 3 things you need to really control to make sure that it works correctly, and provided your fit is good. I mean, we always assume fits. I'm assuming that the fit is good, but yeah, like I think going through the mathematics of it just simplifies it all. You can locate instantly where these things are coming from. Thanks.
Thanks. Anyone else? Phil.
Thank you, Matt, for this great talk. So thinking beyond HMC, normalizing flows are being used in variational-based techniques, optimizing the posteriors, or using SBI to optimize. These are all gradient-based optimizations. Are these considerations needed for those techniques as well, or?
Yeah, so one thing that I didn't really mention, but I think that it could be useful. So for example, if you use SBI to target the likelihood, in Hamiltonian Monte Carlo, it's you're taking the log probability, so you just get the sum of different terms. So you have the sum of a likelihood, sum of a prior. So if you have a normalizing flow anywhere in that sum, you need to consider this. So I'm not sure how many people are actually doing this, but for example, if you learned the likelihood function and then wanted to include that into a differentiable Hamiltonian Monte Carlo pipeline, your architecture would need to match this. Because it's an architectural, it's based completely on the architecture. If you use a normalizing flow with any of those conditions that don't match it, if you put it into, even if you just put it into any sort of minimization algorithm, it's going to have problems. But in terms of, I haven't thought about it in terms of actually, I don't think it's an issue in terms of, SBI, because SBI, they tend to target posterior or the likelihood itself from there. And then they care more about sampling from that distribution. So everything tends to be fine. Or if you just, if you just wanted to, populate, I think Doug said the other day, actually, in this group meeting, is sometimes you can just populate that space and look at the prior probability. So this isn't the only way to use inference, particularly with a normalizing flow prior, but it's extremely quick. And if you can get it right, it's amazing.
Still have time for maybe one quick question, after which people are welcome to stick around and talk to the speakers. Did you have one? I thought I saw your hand.
I have several, but I'll just talk about it.
Okay. We're gonna miss all that discussion. Anyone? All right. Well, if not, then discussion is open for whoever wants to
Thank you
stay.
very much.
So much. Thank you.
Yeah, thanks for the talk.